right, our next proof is a direct proof, and we want to prove that 51 is not a prime number. So what do we need to do? We need to take a look at some of the factors of 51. So 51 factors into a 3 and a 17. So 51 can be divided by 1, 3, 17, and 51, but I don't write that down. Therefore, it is not a prime number because it is divisible by more than 2 natural numbers. And we're using the definition of prime numbers here. Next, I want to prove that 8 is an element of the even numbers. Remember that any even number takes the form 2n. So if a is an element of the even numbers, then 2n would be what a looks like. So 8 is 2 times 4, and 4 is an element of the integers. So 8 is an element of the even numbers. So 8 is an element of e. Next, I want to prove that if x is an even number and y is an even number, then if I add those two numbers together, I'm going to get back out an even number. So, if x is an element of the even numbers, we can write x as 2n. So x equals 2n, where n is an element of the integers. If y is an element of the even numbers, then we can write y as 2 times m, where m is an integer. If I take 2m plus 2n, I can go ahead and factor out a 2 from this. So that can be 2 times m plus n. And m plus n is an integer because if I add any two integers, I always get an integer back out. So x plus y is an element of the even numbers because you can write it as 2 times m plus n. So x plus y is an element of the even numbers. Next, I want to prove that if x is an even number and y is an even number, then x times y, so the product of x and y, is an even number. So if x is an element of the even numbers, we can write x as 2n, and n is an integer. If y is an even number, we can write y as 2m, where m is an integer. So xy equals 2n times 2n, so we'd get 4mn, and I can go ahead and factor out a 2. So that gives me 2 times 2m plus n. Well, 2m times n, that's going to be an even number, but that's also going to be an integer. So x plus y, x times y equals 2 times 2mn, and it's of the form of an even number, so it's an element of the even numbers. Our next and last direct proof I'm going to do in this class, in this section, is that let n be an element of z. I want to prove that n plus 2 divides n squared minus n minus z. So what are we going to need to do is we're going to need to factor like we did in college algebra. So we want to find the factors of AC that add up to b. So, because n is an element of z, we know, how is this going to factor? Well, I want to find the factors of AC that add up to b. So the factors of AC, which is -6, that add up to b, which is -1, are -3 and 2. So this is going to factor to n plus 2 and n minus 3. And if you don't remember how to do this, you'll need to go back and look at College Algebra Text section 5.2. If you, for some reason, don't have that text anymore, let me know and I can upload those videos. I'm happy to help. So because n is an element of z, we know that n plus 2 is an element of z, and n minus 3 is also an element of z. So because n squared minus n minus 6 can be written as n plus 2 times n minus 3, by definition, 3.1.1, the definition of division, n plus 2 divides n squared minus n minus 6 because there exists a n minus 3, right, that we can multiply it by. That's our k from the definition of 3.1. Let's talk about a couple more propositions. So if x is a real number, remember that means it could be a fraction, it could be an irrational number, it could be negative, it could be positive. And as long as x is greater than 1, then x squared is greater than or equal to x. Why don't we go ahead and prove this proposition? So let's go ahead and say that if x is greater than 1, then x is greater than 1. I need to get it to look like this. How can I make this look like this? So we can multiply both sides by, because this is greater than 0, I could multiply both sides of this by x. So 5x times x is greater than x, because I also know that x is greater than or equal to x, times 1. That gives me x squared is greater than or equal to x, so thus this is going to hold true. I also have proposition 3.13, and this says that if c divides m and c divides n, then c divides m plus n. So let's take a look at that. Let's come up with some examples. So let's say that 3 divides 9 and 3 divides 6. Then 3 divides 9 plus 6, which is 15. And that holds true. Okay? Our next proposition is that suppose x is an element of z. If x squared minus 6x plus 5 is an even integer, then x is an odd integer. How am I going to go about proving this? Okay, so let's let x equal 2m. So instead of having x be odd, let's let x be an even number. I'm going to prove that this would have to then also be odd. So if I have x squared minus 6x plus 5, that's going to equal to 2m squared minus 6 times 2m plus 5. This gives me 4m. I don't want to write it like that. That's going to give me, well, maybe I will, 4m squared minus 12m plus 5. I need to figure out how to write this so it looks like an odd number. Right? So I could pull out that 1. So I've got 4m squared minus 12m plus 4 plus 1. And then I could pull a factor of 2 out of this. So I'd get 2 times 2m squared minus 12m minus 6m plus 2. So if x is even, then x squared minus 6x plus 5 is odd. So I proved the opposite. This is an example of the contrapositive. So let's take a look at the definition of contrapositive.